Alright, this is a supplementary video to go along with the main notes for section 4.0 because after I made the original video, I at some point added just some other examples to our notes handout. So this video is basically just going to be going over those other examples so you can finish your notes, okay? So you already went through this stuff just to find the greatest common factor. You're going to find the GCF, or greatest common factor of the numbers, and then of the variables separately, but then you're just going to multiply them together. So you already went through this stuff to where if you want to find the greatest common factor of these two monomials, you would first figure out the greatest common factor of like the numbers, or the coefficients I could call them, and that's just 3. And then the greatest common factor of x to the second power and x to the fourth power just ended up being x to the second power. And I would have to think that I mentioned in the previous video, the partner video, that all you really got to do with the variable stuff is just go with the smaller of the 2 or more, or 3 powers. Or what if you're taking the GCF of only 2 monomials, it's the smallest exponent in both of them. Or if there was a third trinomial, or sorry, third monomial, basically the overall, it's the smallest power for that variable. And then so if you want to find the greatest common factor of y to the 5th, and just y, or technically y to the 1st, you just go with the smallest power, y to the 1st, and then you just put it all together. The overall GCF, like we went over, is that. I'm going to have to write with my mouse here. Okay. We'll go with purple, and we'll go with this size. Okay. Alright, so so these other examples, this is the main reason for this second video, you know. What's the best way to figure, because the variable part's going to be easy. In fact, like, to get that out of the way, if we're comparing x to the 4th and x to the 4th, what's the smaller power? Well, it's a tie. So x to the 4th, sorry, this is going to be kind of sloppy in this video with my mouse. And then y to the 2nd and y to the 3rd, the smaller power is y to the 2nd. So that's out of the way. When it comes to 18 and 6, like the normal regular numbers that you've been dealing with since you knew what numbers were, kindergarten or earlier, that's actually can be the tougher part, you know. And I don't want to open up like a huge can of worms maybe here, but if you can just do this in your head, I mean, that's probably ideal. If the numbers are small enough, or that where your mental math abilities can just figure out like what is the largest factor that 18 and 6 both have. In other words, what's the biggest number that can be divided cleanly into both 18 and 6? Like, I can do it. It's 6. And so this problem can be over and done with right now. Okay? And I don't know, in this video, I don't know if I want to go there to where, like, the longer way that, almost like you could think of it as a backup method if you can't just do this in your head, right? So maybe we'll circle back to that method, maybe. So number 2, all right, 24 and 16. Let's just try to do this in our head. What's the biggest factor that they both have? What's the largest number that can be divided into both of these? Now, the first candidate is 16, because 16 divides into 16, but it doesn't divide into 24. So what might be the next possibility that could divide into both of these? A few more seconds for you to think of it. I'm going to go with 8. I think 8 is the largest or greatest common factor. And then with the variables, x to the first power, because technically there's a 1 there, and x to the third, you're just going to go with the smaller power. Y to the fifth and y to the fourth, that's the greatest common factor. And then, ooh, here we go. I don't know if I talked about this in the previous video, or the initial video. This monomial has a factor of z to the first. This over here has no z at all. This doesn't have a factor of z. In fact, if you want to think of it like this, it's totally invisible, like big time invisible, like technically not even there kind of thing, but you can think of it being like z to the 0, or again, like no z at all, no factor of z. And of course, what's the smaller of the two? No z at all. So the overall GCF contains no z at all. And then we moved on to, in the video, the kind of the other side of this, least common multiple. And likewise, you're just going to do the same sort of routine. You're going to find the, whoa, I didn't have this pre-written in here. Well, we did this in the other video. You'd find the overall, see, this is different. This is kind of a different vibe. This is now least common multiple. We're still looking for things they have in common, but now we're looking for multiples that they have in common. And in the previous video, we talked about all the multiples of 3 and all the multiples of 4. And now we're looking for the smallest common multiple. And then I probably mentioned how now with this, when you compare, like, say, x to the third and x to the fifth, you're looking to go with the larger of the two powers, or the largest of all the powers for each variable. So now again, the main reason for this second video is these other examples that were added to the handout. So then once again, I mean, just the same routine, just with like kind of different things, factors, multiples. We're going to be trying to do this in our head if we can. So if you're thinking of like all the multiples of 12, and there's an endless number of them, like the multiples of 12 go on forever, just like the multiples of 10 go on forever, like 10, 20, 30, 40, 50, 60, 70, 80, ... literally forever. We just want the least one that they both have in common. And the first candidate is literally 12, because 12 is a multiple of 12, but not also of 10. So when do these multiples meet? And again, if you can do this in your head, like I can, at least with numbers this small, it ends up being 60, okay? And again, like there is a fallback method that I hesitate to get into, because ideally you want to be able to do this in your head. I mean, man, life is so much easier. Because then what? We can move on to the variables, and then x to the second and x to the fourth. This is just something you got to get in the habit of remembering. You're just going to go with the larger power, okay? And then y to the third and y to the third. It's a tie. And that one's done, as long as you can, kind of do that in your head. This next example, I guess the final example, 24 and 8. What's the smallest multiple that they both have? Remember, the multiples of 24 go like 24, 48, 72, so on and so forth. And then for 8, it goes like 8, and then 16, and then 24, and then 32, and then 40, So what do you think the smallest common multiple of both? Can you do that in your head? Give you a few more seconds. It ends up being 24. Remember, 24 is a multiple of 24, so don't forget to factor that in. Pun intended. And then we move on to the variables. X and x to the third. Which one's larger? Which one has the larger power? Well, of course, 3 is larger than, technically, it's a 1 there. And then y to the 5th and y to the 4th, you're going to go with the larger one with multiples. Multiples are big, people. Multiples get big. Factors get small. And then, okay, let's see what happens now with the z's, where this one has z to the 2nd power, and this one has no z at all. But here we're going with the bigger one. So what's bigger, 2nd power or technically 0 power? Well, 2nd power. All right, well, I mean, since we have time, right? You have time. Let's talk about this other method, and for that I will completely change color. What color should I use? Pink, good choice. All right, so again, the variables are easy. I don't need to break it down for the variables. In fact, I don't want to get too far ahead of myself, but as I show you this backup method for the numbers, it's actually going to lead to this easy exponent situation that we have for the variables. Anyway, so here we go, 18. Your method here is to kind of break down 18 into all of its prime factors, like essentially its prime factorization. So we just start breaking it down. It doesn't matter how, okay? And then, you know, we have like, and again, sorry, this is going to be sloppy because I'm writing with my mouse. And so when you break down 18 to its prime factors, it ends up being 3 times 3 times 2. In other words, 3 to the 2nd power times 2. So this is the prime factor sort of way, the prime factorization way, to just write 18. 18 and 3 squared times 2, literally the same. And then we're going to want, oh my God, that's too sloppy. And then 6 breaks down pretty quick into just, because I can't break either of those down anymore. So we have 3 times 2. In other words, 3 to the 1st power times, what did I say? Did I say it right? 3 to the 1st power times 2 to the 1st power, technically. So now okay, so here's the punchline, right? If you're able to do that, I know it takes more time, but hey, if you can't do this in your head, you got to do it some way. So now that we have it written as like a prime factorization, now we can compare 3's and 2's just like we were comparing x's and y's. So 3 to the 2nd power and 3 to the 1st power. Now here in these examples, we're trying to do greatest common factor. So we're going with the smallest one. So 3 to the 2nd compared with 3 to the 1st, we're going with 3 to the 1st. Now the 2's. 2 to the 1st, technically, and 2 to the 1st, well, it's a tie. So there we go. There's the overall GCF of 18 and 6. 3 to the 1st times 2 to the 1st, which, what does that equal? 6. Let's do that here. So let's start with 24. Again, once again, too sloppy. Man, 2's and 6's are tough. Oh my gosh. It's not funny. It's not funny. All right, so again, it doesn't matter how we break this down. We could even start with like just 2 and 12. So that there's no way that can break down anymore. And then we have like 6 and 2. There's a challenge for oh geez. All right, so I think that's broken down right. So 24 is essentially 2 times 3 times 2 times 2. In other words, 2 to the 3rd power times 3, or 3 to the 1st power. And then we have 16. Again, remember, we know where this is headed, but all right, so it doesn't matter. We could do 4 and 4 to start this breakdown. We could do 2 and 8. Of course, 4 breaks down to 2 times 2. And same with, and so we have basically, those are done, so I circle them. So 16 is basically 2 to the 4th power, and that's it. You know, if you want to write, well, there's no 3's, so you could technically think of it as 3 to the 0 power, but all right, so now we compare these 2's and 3's and stuff the same way we were comparing x's and y's and z's. So again, greatest common factor, so we're looking for the smaller power we have with the, so 2 to the 3rd, 2 to the 4th, we got to go with 2 to the 3rd. And then we have, this one has a 3 to the 1st power, this one has no 3 at all. So what goes in the overall greatest common factor? What's smaller? No 3 at all. So guess what? That's the greatest common factor of 24 and 16. And what is that equal to? You guessed it, 8. So again, that's the secondary, longer way to do it if you can't just do it in your head. So now let's do it with least common multiple. Okay? So once again, we're going to break down 12 into either 2 and 6, but I'm going to go with 3 and 4 instead. That one's done. And now that we break down the 4, all right. So 12 is basically, that's too messy, 2 to the 2nd power, because it's 2 times 3. And now 10, we're going to break down 10. It's ugly. 5, literally the only way to do this is 5 times 2. And guess what? That's done. Can't break down 5 anymore. Can't break down 2 anymore. So literally 5 to the 1st power, technically to the 1st power, times 2 to the 1st power. And now we compare. But look, this is now least common multiple. So with the x's and y's and maybe z's, or just the variables, now we're going with the largest power we have for each. So now we're going to treat the 2's and the 3's and the 5's just like the x's, y's, and z's. So this one has a 2 to the 2nd. This other one has a 2 to the 1st. So we go with the largest one, 2 to the 2nd. Now 3's. This one has a 3 to the 1st. This other one has no 3 at all. Well, what's bigger? 3 to the 1st. This one has no 5 at all. This one has 5 to the 1st. So if we're going to go with 5 to the 1st. So this is the overall least common multiple of 12 and 10, which guess what? That's 4. 4 times 3 times 5. Guess what that equals? 60. So it's just another way you can come up with the least common multiple of the numbers. Let's do this last one, okay? 24. That's pretty good too. Let's go with 6 and 4 because I'm smart. I'm going to make this the shortest factor tree possible. If I went with 2 times 12, I'd be branching off more. But it doesn't matter. You can do what you want. You can do it however you want. So those are all done, I believe. So 24 is essentially 2 times 3 times 2 times 2. In other words, 2 to the 3rd power times 3. And then 8. Oh, geez. That's obnoxious. I think we kind of have to go with 2 times 4, eh? Yeah. Getting some deja vu here. Didn't we already do this with 8 back here? No? Where was 2 to the 3rd? What was I thinking there? Maybe here. Maybe I was thinking of this part of it. Sorry. So 8 is essentially 2 to the 3rd. So again, for this overall LCM, now we're looking to take the largest. So 2 to the 3rd. This one has 2 to the 3rd. So we're going with the largest power, and it's a tie. And this one has 3 to the 1st. This one has no 3 at all. But we're going to go with the largest one. So here we go. This is 2 to the 3rd times 3. literally equals 24. So yeah, there we go. So that now you have complete 4.0 notes.